In 5.6a, we're going to talk about properties of square roots. So let's review what square roots are first of all. Important to remember, for example, what it looks like. The square root of 9 means what number 2 times is 9. The answer would be 3. So that's what a square root is called. In terms of the symbols, this symbol right here is called the radical symbol. The number underneath the radical, for example, the number 9 is called the radicand. So let's go look at some properties of square roots and their radicals. One other thing that's handy to know is if, for example, you have the square root of a times b, you can actually pull that apart. So that would be a times the square root of b. That's helpful for if you have the number such as the square root of 27. There is not a nice square root of 27, but 27 is the same as the square root of 3 times the square root of 9, because 9 and 3 make 27. Well, then what's handy, I know the square root of 9. That number is actually a 3, so we can change it to a 3. This square root of 3 still stays the same. Now, the quotient property says if you have the square root of a over b, you can actually break that up into two things too. You can do the square root of a over the square root of b. Now that's handy in an example like this. What is the square root of 5 over 36? I have no idea what number 2 times is 5 over 36. However, if I break this up and do the square root of 5 over the square root of 36, what I do know is that the square root of 36 is the number 6. I don't know the square root of 5, so I just keep it. So if we apply these properties, let's look at letter A. They want to know the square root of 40. There's not a number, if I multiply it 2 times by itself, that gets me 40. But if I think of the multiples of 40, or the factors, are there two numbers such that one of those numbers is a nice perfect square root? What about 4 and 10? So I know that, so I can use the property and pull them apart. Square root of 4, square root of 10. Now, the square root of 4 is the number 2, so I change that to a 2. The square root of 10, I don't know. There isn't a nice one, so I just keep it as a square root of 10. This is called a simplified radical, where you pull out all the nice perfect square roots that you can. Okay, if we look at letter B, is there a nice square root of 3? No. Is there a nice square root of 15? There's not. This is multiplying two radicals together, so I can crunch it together and reverse it and do 3 times 15, which is going to be the square root of 45. Now, unfortunately, the square root of 45, there isn't one number twice that when you multiply it, you get 45. However, there are two factors of 45. One of them is a nice perfect square root number. If you can think about it, it's 9 and 5. So now I can actually pull them apart and do the square root of 9 times the square root of 5. Well, the square root of 9, that's the number 3, so I actually change it. The square root of 5, there isn't a nice one, so I keep it. We call this 3 times the square root of 5 as the final answer. Now, letter C, the square root of 49 over 81, I'm not sure about that fraction, but the nice thing is I can break it into two normal numbers. I can do the square root of 49 over the square root of 81. Well, that's easy. What number twice is 49? That's 7. 81, what number twice is 81? That's 9. Notice when I take the actual square root, for example, of 81, that radical symbol goes away. And make sure you do that. If you know the actual answer, the radical drops and you just get the normal integer value. Okay, letter D is similar. This looks pretty complicated, written as a square root of 7 over 144. So I'm going to see if it helps me to break it into two. Square root of 7 over square root of 144. And if you don't know, just type in your calculator the square root of 7. If you get a nice whole number, then there's a nice answer. If not, then you just keep it. The square root of 7 is not a nice whole answer, so I'm just keep it as a square root of 7. The square root of 144 actually is a number. There is a number if I multiply it twice by itself, I get 144, and it's 12. What you would do again in the calculator, just type in the square root of 144 and it should kick back 12. And that is our final answer. Let's look at a couple more. The square root of 50. Now there's not a number that I multiply twice that gets me 50, but there is a perfect square root within 50. There's two multiples. Now first my brain goes to 5 and 10, but the square root of 5 isn't a good one, nor is the square root of 10. So I'm going to actually cancel that. It's not that. What it is, it's 25 and 2. That's 50. So now break it into the square root of 25 times the square root of 2. Square root of 25 is actually the number 5, so notice I drop the square root symbol and make it a 5. The square root of 2, it's not a nice whole number. It's actually 1.414 in your calculator, so I'm going to keep it and write it as 5 square roots of 2. Now, the square root of 6 is not a nice number, nor is the square root of 10. So they're being multiplied, so I'm going to crunch it together and make it 60. Now, I want to think of multiples that are nice perfect squares that might work with 60, so I'm going to jot some down. I know 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared 25. And I'm wondering if any of these numbers, if I multiply it by something else, will get me 60. And I think I got it. It's going to be the 4. So I can rewrite this as 4 times 15. Therefore, I can break it up, square root of 4 times the square root of 15. Square root of 4 is the number 2. Square root of 15, there's nothing nice. So I just keep it, and that's our simplified answer. Now, if you had a hard time following that, there's a second method to simplifying radicals that some people really like. It's called the factor tree method, and here's how it works. I'm going to redo this last two problems again. What you do is you break it down no matter what numbers at first come to mind. Remember I said 5 and 10 for 50? I'm going to do that again. So now you keep breaking it down. Can you break down 5 any further? Other than 5 times 1. I can't, so I'm going to circle that. How about 10? 10 can be 5 and 2. Okay. Can 5 be broken down further? It's not because it's prime, and 2, neither can 2. So what you've noticed are the 3 numbers I boxed in blue make up the total of 50. So here's how this works. You look for pairs of numbers. So what I notice is that the 5 happens twice. So what I can do is say this 5 and this 5 are a group. So I pull it out and put it on the outside. So that's now used. What's ever left over has to stay under the square root symbol. So the 2 is left over, and that's our final answer. Okay, let's look at 60 the same way. So let me bring them back together first of all. This was the square root of 60. Now for me, 6 and 10 first comes to my mind, so I'm going to do 6 and 10. Neither of those are nice perfect squares, by the way. 6 can go further, 3 and 2. 10 can go further into 5 and 2. And I think we have them all. So I'm going to put little boxes around them so I know those are the final last numbers. What that means, by the way, is 3 times 2 times 5 times 2 gets me the 60 up here. Now if you see any pairs, which I do, there's a pair of 2s. So that pair of 2s I'm going to say is gone and used. I'm going to put that on the outside. There's no other pairs of numbers, so all you do is you take what's left over, which is the 3 and the 5, you keep that under the radical symbol, and you just multiply them back together. 3 times 5 is 15. Factor tree method is actually a quite handy way to simplify radicals if you're really struggling and trying to find nice perfect squares. Especially with like 60, people can't always see it. Just do a factor tree and it will actually tell you the answer.